For most of human history, the night sky has inspired one haunting question. If the universe is so vast, so old, and filled with billions of stars and planets, where is everybody? Tonight we explore one of the greatest mysteries in science, the Great Silence. From distant galaxies and potentially habitable worlds to the possibility of advanced civilizations that may have risen and vanished long before humanity appeared, the cosmos seems strangely quiet. What scientists have discovered is both fascinating and deeply unsettling. The answer may reveal something profound about life intelligence and the future of our own civilization. Before settling in, take a moment to like this video and subscribe to Cosmic Bedtime Stories. Every subscription helps bring more relaxing journeys through space science and the mysteries of the universe. Now dim the lights, get comfortable and drift into the silence of the cosmos as we uncover the terrifying truth behind the Great Silence. Section 1. On the largest observable scale, the universe presents a structure that appears both vast and faint, where light and matter are spread across distances so extreme that any local activity becomes diluted into near silence. This silence is not an absence of events, but a consequence of scale, where radiation from countless galaxies arrives, weakened, stretched, and indistinct. At this scale, even energetic processes such as supernovae or quasar emissions are separated by such immense distances that their signals rarely overlap in any meaningful way. The observable universe itself contains billions of galaxies arranged in a web-like pattern, yet most of this structure is empty space where matter density is extremely low. Photons, the fundamental particles of light, travel across these immense distances, gradually losing energy as space expands, which further contributes to the perception of quiet. Even though activity is constant at smaller scales, the overall structure of the universe creates an environment where interactions become rare when viewed from a cosmic perspective. This leads to a form of observational silence where signals exist but are so widely dispersed that they blend into a uniform background. The scale of separation between galaxy clusters is so large that even light takes millions of years to cross these gaps. As a result, the universe appears quiet, not because it lacks activity, but because the transmission of information is limited by distance and time. On the grandest scale, structure and emptiness coexist, creating a background that appears static to any observer confined within a limited region. This perceived stillness is a natural outcome of cosmic expansion and the distribution of matter across space-time. Large-scale surveys of the sky confirm that matter is clumped into filaments and nodes, separated by vast voids. Within these voids, regions of space contain so few particles that interactions become statistically improbable over long periods. This statistical scarcity reinforces the impression that the universe is quiet even though activity persists at all scales. At the boundary of observational reach, the universe also demonstrates limitations imposed by finite light speed, where distant regions are seen only as they existed in deep past time. This time delay means that different regions of space do not share a simultaneous present, further reinforcing the sense of isolation across cosmic distances. The expansion of space itself stretches wavelengths of light, a process known as redshift, which gradually shifts information toward lower energy forms. As redshift increases with distance, the oldest and most distant galaxies become increasingly difficult to detect, contributing to the impression of a fading universe. Cosmic background radiation fills all directions, a faint afterglow of the early universe that remains nearly uniform across the sky. Small fluctuations in this background represent the earliest seeds of structure, yet they are extremely subtle and require precise instruments to observe. These faint variations eventually led to the formation of galaxies, but at the larger scale they still appear as almost uniform noise. The distribution of dark matter, an unseen form of mass inferred through gravitational effects, shapes the cosmic web while remaining invisible to direct observation. Because dark matter does not emit or absorb light, it contributes to structure without adding visible brightness, reinforcing the overall sense of emptiness. Galactic clusters themselves are gravitationally bound systems, yet they drift slowly within a larger cosmic expansion that stretches space between them. This combination of binding and expansion produces a universe where structure exists, but communication across structure remains limited. Even powerful radio signals emitted from distant civilizations would spread and weaken dramatically as they travel across intergalactic distances. At such scales, the energy required to maintain detectable communication becomes enormous, limiting any persistent exchange of information. The observable universe therefore functions as a vast stage where activity is continuous, but rarely intersecting across great distances. This rare intersection of signals contributes strongly to the perception that space is silent despite its ongoing dynamic processes. Ultimately, the largest scale of existence presents a universe that is active in every direction, yet appears uniformly quiet to observation. This uniform quietness is reinforced by the limits of human observation, which can only capture light that has had enough time to reach detectors across cosmic distances. Regions beyond the observable horizon remain entirely unknown, as their light has not yet reached any current point of detection. This horizon defines a fundamental boundary to knowledge not as a physical wall, but as a limit imposed by time and expansion. Within this limit, the universe appears consistent and uniform at large scales, a principle known as cosmic homogeneity. Homogeneity means that on average matter is distributed evenly when viewed across sufficiently vast regions of space. Even so, local variations still exist, but they are statistically minor compared to the scale of the universe itself. This statistical dominance of emptiness over structure contributes to the overwhelming impression of silence across cosmic observation. Even when energy events occur, their signals disperse so widely that they rarely form coherent patterns at intergalactic distances. The universe at this scale is therefore best understood not as empty but as overwhelmingly diffuse and separated. This diffusion reduces the likelihood of any direct interaction between distant regions, making the cosmos appear quiet even when it is active. Light itself, while fast on human scales, still requires vast spans of time to bridge intergalactic distances. This delay ensures that the universe is always observed in a state of partial history rather than simultaneous reality. At the same time, gravitational structures evolve, slowly reinforcing the stability of large-scale cosmic patterns. This stability contributes to the impression that the universe is unchanging when observed from extreme distances. However, on smaller scales within galaxies, constant motion and transformation continue without interruption. This contrast between small-scale activity and large-scale emptiness is central to the perception of cosmic silence. The universe therefore appears both dynamic and silent, depending entirely on the scale at which it is observed. This duality of activity and silence defines the observable universe at its largest extent. At this point, the structure of cosmic silence emerges as a fundamental feature of scale rather than a lack of events. This feature arises naturally from the way matter, energy, and space-time are distributed across the observable cosmos. Section 2. The cosmic microwave background forms a faint, almost uniform glow that fills every direction of space, representing the oldest detectable light in the universe. It emerges from a period when the universe was still hot and dense enough for photons and matter to remain tightly coupled before atoms could form in stable configurations. As expansion continues, that early radiation stretches across time and space, gradually losing energy and shifting into the microwave region of the electromagnetic spectrum. This transformation does not remove the signal, but spreads it so thinly that it becomes extremely difficult to detect without highly sensitive instruments. The cosmic microwave background appears today as a nearly uniform temperature field, measured in all directions with only tiny variations that reflect the earliest density fluctuations of matter. These variations are extremely small compared to the overall uniformity, yet they contain the seeds of all later cosmic structure. On a large scale, this background acts as a persistent layer of ancient information that surrounds all later formations in the universe. It exists far beyond any individual galaxy or cluster, forming a universal reference field that predates all stars and planets. At this stage of cosmic observation, silence takes on a different form. It is no longer only the result of distance between galaxies, but also the consequence of a background radiation field that is extremely uniform and smooth. Because the variations in this radiation are so subtle, the early universe appears almost featureless when viewed through this lens. Instruments detect temperature differences measured in fractions of a degree, revealing only slight imprints of primordial density changes. These imprints represent regions where matter was marginally more concentrated, eventually leading to gravitational collapse and the formation of galaxies. Despite this significance, the variations remain so faint that the background appears visually still. This stillness is not emptiness, but a frozen record of the universe's earliest conditions. The cosmic microwave background also establishes a kind of observational horizon. It marks the point beyond which light cannot directly reveal earlier structures, because the universe was opaque before the formation of neutral atoms. Before this transition, photons continuously scattered off charged particles, preventing any clear transmission of information. Once atoms formed and the universe became transparent, light began to travel freely, creating the background radiation observed today. This transition defines a boundary in observable history beyond which direct electromagnetic information cannot pass. As a result, the background acts as a veil over the earliest phases of cosmic evolution. As space expands, the wavelength of this radiation stretches further, causing it to cool steadily over time. This cooling process is gradual and ongoing, meaning that the background today is significantly colder than it was at the time of its origin. The temperature now measured is only a few degrees above absolute zero, a level so low that it blends into the natural thermal environment of deep space. This extreme cooling contributes to the impression of silence, since thermal radiation at such low energy carries very little dynamic influence on surrounding structures. It exists as a passive field rather than an active driver of change at large scales. The cosmic microwave background is also remarkably isotropic, meaning it appears almost identical in all directions. This uniformity suggests that the early universe was highly homogeneous on large scales, with only minor fluctuations that later grew into cosmic structure. The near-perfect symmetry of this background reinforces the sense that the universe, at its earliest observable stage, was calm and evenly distributed. Small irregularities embedded within this uniform field are carefully studied to understand the origin of galaxies and clusters, but they remain secondary to the overwhelming smoothness of the background itself. This smoothness gives the impression of a silent foundation underlying all later cosmic activity. Dark matter influences this stage indirectly through gravitational effects on the tiny fluctuations present in the background radiation. Although it cannot be observed directly, its presence is inferred from the way matter later clusters into large-scale structures. The cosmic microwave background carries subtle signatures of these interactions, encoded in the pattern of temperature variations across the sky. These patterns are not visible to the naked eye, but are reconstructed through precise measurements and statistical analysis. Even so, the overall impression remains one of uniformity and stillness, as the variations are extremely small compared to the scale of the background itself. The photons that form this background travel freely through space without significant interaction, gradually filling the universe with a faint continuous glow. Over billions of years they have spread so widely that they now occupy every region of observable space. This creates a persistent radiation field that is present everywhere, regardless of local cosmic structures. Galaxies, stars, and planets exist within this field, yet it remains largely unaffected by their presence. This independence reinforces the sense that the background is a separate layer of reality existing beneath all visible structures. At the level of observation, the cosmic microwave background provides a snapshot of the universe at a very early stage, frozen in time and preserved through expansion. It allows scientists to infer conditions that existed long before any stars formed. Despite its importance, it contributes to the overall silence of the cosmos, because it carries no sharp structures or dynamic variations at large scales. Instead, it behaves as a diffuse uniform glow that blends into the emptiness of space. This uniformity reduces contrast between regions, making the universe appear visually calm. The interaction between this radiation field and later cosmic structures is minimal. Matter clumps into galaxies and stars without significantly altering the background itself. As a result, the background remains a stable reference layer against which all later activity occurs. It does not evolve rapidly in response to local events, and its slow change is driven primarily by universal expansion rather than local dynamics. This separation between background and structure contributes to the layered nature of cosmic silence, where early conditions persist beneath all subsequent complexity. In the broader context of the universe, the cosmic microwave background represents both origin and limitation. It is the earliest visible boundary of observation, and also a constant reminder of the universe's uniform beginnings. Its presence defines a threshold beyond which direct observation cannot reach, marking a fundamental constraint on knowledge. Within this constraint, the universe appears orderly and consistent at its largest scale, with no abrupt transitions or discontinuities visible beyond the background layer. This consistency strengthens the perception of a quiet cosmos, where even the earliest light has been stretched into near uniformity. The background continues to drift through space as the universe expands, maintaining its faint presence everywhere. Its energy gradually decreases, but its structure remains stable in form. Over immense timescales, it will continue to fade further, blending even more deeply into the cosmic environment. For now, it remains one of the most important and subtle features of the universe, a silent echo of its earliest moment of transparency. This echo carries no sound and no motion, only the trace of ancient conditions preserved in radiation. It forms a continuous invisible layer beneath all observable structures, reinforcing the impression that the universe, despite its activity, remains profoundly still when viewed at the largest scale. Section 3. Between galaxies lies the intergalactic medium, a vast region of space that contains extremely low densities of matter, primarily hydrogen atoms and ions separated by enormous distances. This medium is not empty in a strict sense, yet its sparsity makes interactions between particles exceedingly rare. On this scale, a single atom can be separated from another by distances far greater than those found within galaxies, creating an environment where collisions are statistically uncommon over long periods of time. The intergalactic medium fills the space between the cosmic web's major structures, extending through filaments and into large voids where matter density drops even further. These voids occupy most of the universe's volume-forming regions, where only a few scattered particles exist per cubic meter. The result is a near vacuum that stretches across billions of light-years, contributing significantly to the perception of cosmic silence. In these regions, gas exists primarily in ionized form, meaning atoms have lost or gained electrons due to exposure to radiation from distant galaxies and quasars. This ionization keeps the gas extremely diffuse and prevents it from forming dense clouds under normal conditions. Even though hydrogen is the most abundant element in the universe, its distribution in the intergalactic medium is so thin that it produces almost no detectable emission without long exposure and sensitive instruments. The faint traces that can be observed appear as absorption lines in the spectra of distant light sources, revealing the presence of otherwise invisible matter. These signals are subtle and require precise measurement, reinforcing the idea that most of the universe's matter is spread too thinly to generate noticeable activity. Dark matter plays a dominant role in shaping this environment, even though it does not interact through electromagnetic forces. Its gravitational influence forms the scaffolding of the cosmic web, guiding the distribution of visible matter into filaments and clusters. Between these structures, dark matter extends into vast halos that maintain the overall shape of the universe's large-scale architecture. Despite this influence, dark matter remains completely invisible, contributing no light or radiation to the intergalactic medium. This absence of emission deepens the sense of silence, as the most massive component of cosmic structure does not participate in observable interaction. Within the intergalactic medium, temperature and density vary depending on proximity to galaxies and energetic sources. Near large structures, gas can be heated to extremely high temperatures due to shock waves and radiation reaching millions of degrees while remaining extremely diffuse. Even at these temperatures, the low density prevents the gas from radiating, strongly limiting its visibility. Farther from galaxies, the gas cools and becomes even more rarefied, approaching conditions that resemble a near-perfect vacuum. These gradients exist across immense distances, yet they change so gradually that they appear almost static when viewed on cosmic scales. The motion of particles in this medium is governed by weak gravitational interactions and occasional radiation pressure from distant sources. Without strong local forces, particles drift slowly through space, following the curvature of spacetime shaped by large-scale mass distributions. This slow movement contributes to the impression of stillness, as there are no rapid or concentrated events occurring within most regions of the intergalactic medium. Over time, some particles will gradually accrete onto galaxies, but this process occurs on timescales far longer than typical observational periods. As a result, the medium appears stable and unchanging when observed over shorter intervals. Photons traveling through the intergalactic medium can cover vast distances with minimal interaction. However, over billions of light-years, even these photons may experience scattering or absorption, leading to gradual dimming and redshifting of distant sources. This process reduces the intensity of light from the most remote galaxies, making them increasingly difficult to detect. The fading of these signals contributes to the perception that space is quiet, as fewer detectable sources remain visible at extreme distances. The universe therefore appears less active, not because activity ceases, but because its signals are progressively weakened. The structure of the cosmic web introduces regions of contrast between dense filaments and empty voids. In filaments, galaxies are relatively close together compared to the cosmic average, while in voids, distances between matter concentrations become enormous. These voids dominate the volume of the universe, and within them the intergalactic medium becomes even more sparse. This uneven distribution creates a patchwork of activity and emptiness, where most regions contain little to no detectable interaction. The dominance of empty regions reinforces the overall impression of silence across cosmic space. Even energetic events such as active galactic nuclei and quasars contribute only localized disturbances to the intergalactic medium. Their radiation can ionize surrounding gas and create bubbles of heated plasma, but these effects diminish rapidly with distance. Beyond these zones, the medium returns to its extremely low-density state, unaffected by the distant source. This limited range of influence highlights the isolation of energetic processes in a universe dominated by emptiness. The intergalactic medium also serves as a repository of matter that has been expelled from galaxies through winds and supernova-driven outflows. These processes distribute elements across vast distances, slowly enriching the medium over cosmic time. Despite this enrichment, the overall density remains extremely low, preventing the formation of new structures in most regions. The material is spread too thinly to collapse under gravity, without external influence preserving the diffuse nature of intergalactic space. On the larger scales, the intergalactic medium forms a continuous but faint background of matter that connects all galaxies. It is not a uniform field, but a highly diluted extension of cosmic structure, shaped by gravitational evolution over billions of years. Its presence ensures that space is never completely empty, yet its rarity ensures that it rarely produces observable phenomena. This balance between presence and near invisibility contributes to the perception of a silent universe where matter exists but rarely interacts in detectable ways. The slow evolution of this medium means that changes occur primarily through large-scale cosmic expansion and gradual gravitational accretion. Over time, some regions may become slightly denser, while others become more rarefied, but these changes unfold over immense timescales. From a human perspective, the intergalactic medium appears effectively static, reinforcing the impression of a universe that is quiet and unchanging at its larger scales. This apparent stillness is a direct consequence of extreme dilution and separation of matter. In this vast expanse, silence is not the absence of energy, but the absence of interaction. Particles exist, radiation passes through, and structures exert gravitational influence, yet the probability of meaningful encounters remains extremely low. The intergalactic medium therefore represents one of the most silent regions of the universe, where activity is present but rarely expressed in observable form. It is within this context that the broader cosmic silence becomes more evident, as even the spaces between galaxies contribute to a uniform sense of stillness across the universe. Section 4. The large-scale structure of the universe is organized into a vast cosmic web where galaxies are not randomly scattered, but arranged along elongated filaments that stretch across hundreds of millions of light-years. These filaments intersect at dense nodes where galaxy clusters form, while between them lie immense voids that contain very little matter. This arrangement emerges from the gradual amplification of tiny density fluctuations in the early universe, shaped by gravity acting over billions of years. As matter slowly collapses into these filaments, empty regions expand and become even more rarefied, reinforcing the contrast between structure and emptiness. The result is a universe where most of the volume is occupied by near-vacuum conditions, while most of the observable matter is concentrated into relatively small regions. Within the filaments, galaxies are embedded in streams of dark matter that guide their motion and evolution. These streams act as invisible pathways along which matter accumulates, forming the scaffolding of cosmic structure. Although galaxies appear numerous when viewed in isolation, their spacing within the filaments is still extremely large compared to any scale familiar within a single galaxy. between one galaxy and another, vast stretches of intergalactic space persist, filled only with thin gas and sparse particles. Even within clusters, galaxies are separated by distances so large that direct interactions are relatively rare over long timescales. The voids that separate filaments dominate the universe's volume and contribute strongly to the perception of cosmic silence. These voids are not completely empty, but contain extremely low-density gas and traces of dark matter. The gravitational environment within them is weak, leading to minimal structure formation and very little dynamical activity. Matter that enters these regions tends to remain diffuse, as there is insufficient density to trigger collapse into stars or galaxies. As a result, voids evolve slowly and maintain their emptiness over billions of years. The formation of the cosmic web is driven primarily by dark matter, which does not interact with light but exerts gravitational influence on ordinary matter. In the early universe, small fluctuations in density grew under gravity, causing dark matter to cluster first. Ordinary matter then followed these gravitational wells, forming visible structures along the same patterns. This process created a separation between dense regions and empty regions that has become more pronounced over time. Even though dark matter is invisible, its role in shaping the universe is fundamental to the large-scale distribution of galaxies. Gas within filaments experiences slow flows along gravitational gradients, moving toward denser regions where galaxies form and evolve. These flows are extremely gradual on human timescales, occurring over millions or billions of years. As gas moves inward, it can be heated by compression and shock waves, increasing its temperature while remaining highly diffuse. This heated gas can emit faint radiation, but the emission is often too weak to detect without specialized instruments. Outside these filaments, such flows are absent or extremely weak, leaving the voids largely undisturbed. The boundaries between filaments and voids are not sharp but gradual transitions where density changes slowly over large distances. These transition zones contain intermediate levels of matter, yet still remain far below the densities found within galaxies. In these regions, the balance between gravity and cosmic expansion determines the movement of matter, creating slow shifts in distribution over time. Despite this motion, the overall structure remains stable on large scales, giving the cosmic web a persistent and enduring shape. Galaxies within filaments are influenced not only by local gravity, but also by the large-scale flow of matter along these structures. This flow can lead to gradual merging of galaxies within clusters, forming larger systems over time. However, these processes occur over extremely long timescales, and at any given moment most galaxies remain isolated within their local environments. The interactions that do occur are significant but relatively rare compared to the vast number of galaxies that exist independently within the web. The cosmic web also reflects the influence of cosmic expansion, which continuously stretches space between distant structures. While gravity pulls matter together in filaments and clusters, expansion pushes against this tendency on the larger scales. This balance between attraction and expansion defines the overall geometry of the universe, creating a stable pattern of structure and emptiness. In regions where gravity is dominant, matter collapses into dense systems, while in regions where expansion dominates matter becomes increasingly diffuse. Light traveling through the cosmic web encounters regions of varying density, but most of its journey takes place through near-empty space. As it moves through filaments and voids, it experiences minimal interaction with matter, allowing it to travel vast distances largely unimpeded. However, over extremely long distances, the cumulative effect of expansion stretches this light, reducing its energy and shifting it toward longer wavelengths. This gradual redshift contributes to the fading of distant sources and reinforces the impression of a quiet universe. The distribution of galaxies within the cosmic web also affects how light and signals propagate across space. In dense regions, interactions between galaxies can produce bursts of radiation, but these are localized and do not significantly alter the large-scale background. In contrast, the vast empty regions between filaments allow signals to weaken without interference, making distant activity increasingly difficult to detect. This separation between active and empty regions contributes to the overall sense of isolation across the universe. Over time, the cosmic web continues to evolve as gravity slowly reshapes its structure. However, this evolution is extremely gradual, and the overall pattern remains recognizable over billions of years. Filaments persist as long, thin structures connecting clusters, while voids remain largely empty. This persistence creates a sense of stability on the larger scales, even though continuous change occurs within individual galaxies and clusters. The dominance of empty space within the cosmic web is one of the key reasons the universe appears silent. Even though galaxies and clusters are sites of intense activity, they occupy only a small fraction of the total volume. The vast majority of space contains little matter and few interactions, resulting in a universe where activity is concentrated but widely separated. This separation limits the transmission of signals and reduces the likelihood of overlapping events across large distances. In this structure, silence is not a lack of cosmic events but a consequence of distribution. The universe is active in localized regions but overwhelmingly empty in between. This imbalance between structure and emptiness defines the character of the cosmic web and reinforces the broader theme of a universe that appears quiet when viewed on its larger scales. Section 5 within the Milky Way galaxy. The scale of structure becomes more compact compared to the cosmic web, yet the same underlying pattern of separation and emptiness continues to dominate. The galaxy is a vast rotating system, containing hundreds of billions of stars along with gas dust and dark matter, distributed across a flattened disk and surrounding halo. Even though this environment appears densely populated when viewed from afar, the actual spacing between stars remains immense. The average distance between neighboring stars is measured in light years, meaning that light itself takes years to travel from one stellar system to another. This spacing ensures that direct stellar interactions are extremely rare, preserving a sense of quiet even within a highly active environment. The Milky Way's structure includes several distinct components, each with different densities and levels of activity. The central bulge contains a high concentration of older stars and a supermassive black hole at the core, while the spiral arms contain regions of ongoing star formation. Between these arms lie more diffuse regions where star density is lower and interstellar matter is more spread out. The galactic halo extends far beyond the visible disk and contains sparse clusters of old stars and large amounts of dark matter. Across all these regions, emptiness remains the dominant feature when viewed at scale. The interstellar medium fills the space between stars within the galaxy, consisting of gas and dust at extremely low densities. This medium is not uniform as it contains cold molecular clouds, warm ionized regions, and hot diffuse plasma. Despite this variety, all phases of the interstellar medium are characterized by low particle density compared to any terrestrial environment. Even in dense molecular clouds where stars form, matter is still far more spread out than in ordinary atmospheric conditions. These clouds represent only localized concentrations within a much larger and mostly empty galactic environment. Star formation occurs within these molecular clouds when gravity gradually overcomes internal pressure, allowing regions of gas to collapse. This process is slow and inefficient, meaning that only a small fraction of available gas becomes part of new stars. Most of the interstellar medium remains unconverted, continuing to drift through space in a diffuse state. The formation of stars is therefore a localized event within a much larger context of near-empty space. Once formed stars carve out regions around them through radiation and stellar winds, further shaping the surrounding environment. The spiral structure of the galaxy is maintained by density waves that move through the disk, compressing gas and triggering star formation as they pass. These waves do not consist of fixed material, but are patterns of gravitational compression that travel through the galactic disk. As they move, they briefly increase local density, leading to bursts of star formation in specific regions. Between these regions, space remains relatively quiet, with fewer energetic processes occurring. This alternating pattern of activity and quiet contributes to the overall balance of the galactic environment. The motion of stars within the Milky Way is governed by the combined gravitational influence of visible matter and dark matter. Stars orbit the galactic center along paths that take hundreds of millions of years to complete. These orbits are not perfectly circular, and stars can move through different regions of the galaxy over time. Despite this motion, the overall structure of the galaxy remains stable, with spiral arms and other features persisting over long timescales. This stability reinforces the impression of a slow and steady cosmic environment. Dark matter forms a large invisible halo around the galaxy, extending far beyond the visible disk. Its gravitational influence helps maintain the rotational stability of the galaxy, preventing outer regions from dispersing. Although it dominates the galaxy's total mass, dark matter does not emit or interact with light, making it undetectable except through gravitational effects. This invisibility contributes to the sense that much of the galaxy is structurally present, but observationally silent. The visible stars and gas represent only a small fraction of the total mass influencing galactic dynamics. Within the galaxy, energetic events such as supernovae and stellar winds inject energy into the interstellar medium. These events can create shock waves that heat surrounding gas and distribute heavy elements across space. However, even these powerful processes affect only localized regions and do not significantly alter the large-scale emptiness of the galaxy. After these disturbances dissipate, the interstellar medium returns to a diffuse state, maintaining the overall low-density environment. The distribution of matter within the Milky Way is not uniform, with dense regions concentrated in spiral arms and the central bulge, while vast regions remain sparsely populated. This uneven distribution creates a patchwork of activity and quiet zones throughout the galaxy. Even in active regions, the scale of separation between objects ensures that most of space remains empty. The result is a galaxy that is dynamic in certain areas, but overwhelmingly quiet when considered as a whole system. Radiation within the galaxy travels through this sparse environment with relatively little obstruction. Photons emitted by stars can traverse long distances, gradually interacting with dust and gas, but mostly continuing unimpeded. Over time, this radiation contributes to the overall energy balance of the interstellar medium, but its influence is spread thinly across vast regions. This dispersion of energy reinforces the sense that activity within the galaxy is isolated and separated by large gaps of emptiness. Even though the Milky Way contains a vast number of stars, the probability of close encounters between stellar systems remains extremely low. Over billions of years, gravitational interactions may cause some systems to pass near each other, but such events are rare. Most stars spend their lifetimes in relative isolation, orbiting the galaxy without significant external disturbance. This isolation is a key factor in maintaining the quiet character of the galactic environment. The galactic center represents one of the most active regions, with intense radiation, dense star clusters, and the presence of a supermassive black hole. Despite this activity, the central region occupies a small fraction of the galaxy's total volume. Outside this region, conditions become progressively quieter as density decreases. This contrast between a highly active core and a mostly empty outer structure further emphasizes the uneven distribution of cosmic activity. On the scale of the Milky Way, silence emerges not from absence of processes, but from the overwhelming dominance of space between them. Stars' clouds and energetic events are embedded within a structure that is mostly empty, ensuring that interactions remain limited in scope and frequency. This balance between activity and emptiness defines the character of the galaxy and continues the broader pattern seen across the universe. Section 6. Star formation regions within galaxies represent some of the most active environments in the universe. Yet even here, activity emerges from conditions that are fundamentally sparse and widely separated. These regions form inside large molecular clouds composed primarily of hydrogen molecules mixed with helium and trace amounts of heavier elements. Although these clouds can span dozens or even hundreds of light years, their internal density remains extremely low compared to any environment on Earth. Within this diffuse structure, gravity slowly gathers material into denser pockets, where the process of starbirth can begin. Despite the eventual emergence of intense radiation and energetic processes, the initial state of these regions is dominated by quiet accumulation rather than violent motion. Molecular clouds are structured in complex, uneven ways with filaments, clumps, and voids created by turbulence, magnetic fields, and gravitational instability. This internal structure does not eliminate emptiness, but redistributes it, creating localized zones where matter is slightly more concentrated. Even in the densest cores of these clouds, particles are still separated by vast distances on atomic scales. The apparent brightness of star-forming regions therefore masks a reality of extreme dilution, where visible structures emerge from conditions that are still overwhelmingly empty. As gravitational collapse begins in selected regions, matter slowly falls inward, increasing density and temperature over long periods of time. This process is gradual, often taking millions of years before a protostar becomes fully formed. During this time, most of the surrounding cloud remains unaffected, continuing its diffuse existence. Only a small fraction of the total material participates in star formation, while the majority remains dispersed in the interstellar medium. This inefficiency ensures that even active star-forming regions retain a large amount of empty space. Within collapsing cores, the formation of a protostar marks a transition from diffuse gas to a concentrated energy source. As density increases, pressure and temperature rise until nuclear fusion can eventually begin in the core. Before this ignition, the system is dominated by gravitational energy release, which produces heat and radiation. However, even at this stage, the surrounding environment remains relatively quiet compared to the scale of energy involved in later stellar evolution. The system is localized and its influence does not extend far beyond the immediate region of collapse. Radiation from newly forming stars begins to interact with surrounding gas, gradually altering the structure of the molecular cloud. Ultraviolet radiation can ionize nearby hydrogen, creating expanding regions of ionized gas known as H2 regions. These regions glow faintly due to recombination processes, but they are still embedded within vast amounts of surrounding empty space. Stellar winds further shape these environments by pushing material outward, creating cavities and bubbles within the cloud. Despite these energetic effects, the overall cloud remains largely diffuse. The balance between gravity and radiation determines the efficiency of star formation within these regions. Strong radiation from young stars can disrupt nearby gas, preventing further collapse and limiting the number of stars that can form. This feedback mechanism ensures that star formation is self-regulating and does not consume all available material at once. As a result, molecular clouds persist for extended periods, slowly forming stars over time while maintaining large volumes of low-density space. Clusters of newly formed stars often emerge within the same molecular cloud, creating groups that share similar ages and chemical compositions. These clusters are initially dense but gradually disperse as gravitational interactions and external forces redistribute their members. Over time, individual stars drift away from their birth regions, joining the broader galactic environment. This dispersal contributes to the overall uniformity of the galaxy, spreading stellar populations across vast distances. Even in active star-forming regions, the spatial scale of separation remains large compared to familiar systems. Stars form within pockets of gas that are separated by empty gaps within the same cloud. These gaps ensure that even localized activity occurs within a framework of extensive emptiness. The contrast between bright emission regions and dark surrounding space reinforces the perception that structure emerges from silence rather than replacing it. Magnetic fields within molecular clouds influence the motion of charged particles, guiding the collapse of material along preferred directions. These fields can slow down or redirect the formation process, adding further complexity to an already slow and inefficient system. Despite their influence, magnetic fields do not eliminate the underlying sparsity of the environment. Instead, they shape how matter is distributed within an already diffuse medium. As star formation progresses, feedback from young stars begins to erode the surrounding cloud. Radiation pressure and stellar winds carve out cavities, gradually dispersing remaining gas. This process eventually leads to the dissolution of the molecular cloud, leaving behind a cluster of stars surrounded by increasingly empty space. The life cycle of these regions therefore transitions from diffuse gas to structured clusters, and finally to dispersal into the galactic medium. The energy produced in star-forming regions is significant on local scales, but limited in its reach across the galaxy. Most of the radiation is absorbed or scattered within the cloud itself, preventing large-scale propagation. As a result, these regions remain relatively isolated from one another, separated by vast distances of interstellar space. This isolation ensures that even active zones of star formation do not significantly disrupt the overall quietness of the galaxy. Over long timescales, the cumulative effect of star formation shapes the structure of galaxies by gradually converting diffuse gas into stars. However, because the process is inefficient and slow, large reservoirs of gas remain unconverted at any given time. This ensures that galaxies maintain a balance between structure and emptiness, with star-forming regions representing only localized concentrations within a much larger diffuse environment. The emergence of stars from molecular clouds therefore illustrates a fundamental aspect of cosmic structure. Activity arises within environments that are overwhelmingly empty. Even the most luminous regions of space are built upon a foundation of sparsity where matter is distributed thinly across vast distances. This underlying emptiness persists throughout the process, ensuring that the universe retains its characteristic silence, even in regions of formation and change. Section 7. Planetary system formation begins within the remnants of molecular clouds, after star formation has already reshaped the surrounding environment. A young star forms at the center of a rotating disk of gas and dust known as a protoplanetary disk, which extends across distances comparable to the scale of entire planetary systems. Although this disk appears dense in astronomical images, its actual physical density remains extremely low, with vast regions of empty space between individual particles. The disk is not solid or continuous, but a diffuse structure, where matter gradually interacts through collisions, gravity, and radiation over long timescales. Within this rotating disk, material slowly begins to organize under the influence of gravity and angular momentum. Dust grains collide and stick together, forming larger aggregates that gradually grow into planetesimals. These early building blocks of planets exist within an environment that is still dominated by emptiness, where interactions occur infrequently compared to the total volume of space involved. Even as growth continues, most of the disk remains unaltered, preserving the overall low-density nature of the system. The distribution of material within a protoplanetary disk is not uniform. Inner regions near the star are hotter and contain different chemical compositions compared to the colder outer regions. Temperature gradients determine where certain materials can condense with metals and silicates forming closer to the star, and volatile compounds forming farther away. Despite these variations, the disk remains fundamentally sparse across all regions, with matter spread thinly over vast orbital distances. As planetesimals grow through accretion, they begin to clear their orbits, gradually dominating their local regions of space. This process leads to the formation of protoplanets, which continue to attract surrounding material through gravitational influence. However, even these growing bodies are separated by large distances, ensuring that collisions remain relatively rare events on cosmic timescales. The formation of planets is therefore a slow process occurring within a largely empty orbital environment. Radiation from the central star plays a significant role in shaping the evolution of the disk. High-energy photons can heat and disperse gas, gradually clearing material from inner regions. Stellar winds also contribute to this dispersal, pushing lighter elements outward and reducing the overall density of the disk over time. These processes limit the lifetime of the protoplanetary phase, eventually leaving behind a system of planets and smaller remnants surrounded by empty space. The transition from disk to planetary system marks a shift from diffuse matter to more defined orbital structures. Planets form distinct paths around their host star, but the space between these orbits remains largely empty. Even within mature planetary systems, the majority of volume is unoccupied with solid bodies, occupying only a tiny fraction of available space. This continues the broader cosmic pattern in which structure emerges within vast regions of emptiness. Gravitational interactions between forming planets can lead to orbital adjustments, collisions or ejections from the system. These interactions are significant in shaping final planetary configurations, but occur over long timescales and within an otherwise sparse environment. Many objects are scattered into distant orbits or removed entirely from the system, further increasing the emptiness of the surrounding space. The presence of debris such as asteroids and comets represents leftover material from the formation process. These objects occupy extended regions of space but are widely separated from one another. Even asteroid belts, which appear dense in simplified representations, contain vast distances between individual objects. This reinforces the idea that even residual structures within planetary systems are dominated by empty space. The outer regions of planetary systems, such as distant comet reservoirs, extend far beyond the main planetary orbits. These regions contain icy bodies spread across enormous volumes, forming diffuse shells around the star. Interactions within these outer zones are extremely rare, and objects can remain in stable orbits for billions of years without significant disturbance. This stability contributes to the long-term quietness of planetary systems. Magnetic fields generated by young stars can influence the movement of charged particles within the disk, shaping its structure and evolution. These fields interact with ionized gas, creating complex patterns of flow and alignment. Despite these interactions, the overall density of the environment remains low, and the influence of magnetic forces operates within a largely empty medium. The final architecture of a planetary system reflects the balance between accretion radiation and gravitational dynamics. Once the disk dissipates, the system stabilizes into a configuration of planets, moons, and minor bodies orbiting in vast empty space. This structure is stable over long timescales, with changes occurring slowly and infrequently. The result is a system that appears dynamic in motion but remains quiet in interaction. Even within fully formed planetary systems, the distances between objects are so large that direct encounters are rare. Space probes, if present, travel through regions that are overwhelmingly empty, encountering only occasional particles or fields. This reinforces the perception that planetary systems, while structured and organized, are fundamentally sparse environments. The formation of planets therefore continues the broader cosmic theme of structure emerging from emptiness. From molecular clouds to disks and finally to planetary systems, each stage preserves a high degree of empty space relative to matter. This persistence of sparsity ensures that even regions of active formation remain quiet when viewed at scale. In this context, silence is not a lack of activity but a reflection of spatial distribution. Matter organizes into coherent structures, yet those structures occupy only small fractions of the total volume. The remainder is empty, allowing processes to unfold in isolation without constant interaction. This balance defines the character of planetary systems and contributes to the broader silence observed across the universe. Section 8. The habitable zone around a star represents a narrow region where conditions may allow liquid water to exist on the surface of a planet, depending on atmospheric composition and pressure. This zone is defined by the balance between stellar radiation and planetary distance, where temperatures remain within a range that supports stable liquid phases of water. Although this region is often considered favorable for life, it occupies only a small fraction of the total space within a planetary system. The vast majority of orbital volume lies outside this zone, where temperatures are either too high or too low to support similar conditions. Within the habitable zone, planetary surfaces can experience relatively stable energy input from their host star. However, even within this narrow region, environmental stability depends on many additional factors, including atmospheric composition, magnetic field strength, and geological activity. Planets that fall within the habitable zone may still be entirely inhospitable if these supporting conditions are not present. As a result, the habitable zone is a necessary but not sufficient condition for surface habitability. The spatial scale of the habitable zone is small compared to the full extent of a planetary system. Even in systems with multiple planets, only a limited range of orbital distances falls within this region. This means that most planets exist either too close to or too far from their star to maintain stable surface liquid water. The distribution of planets across these distances contributes to the overall imbalance between potentially habitable regions and the much larger volume of empty or extreme space. Radiation from the host star is the primary energy source that defines the boundaries of the habitable zone. This radiation decreases in intensity with distance, following an inverse relationship that determines how much energy reaches a planetary surface. As distance increases, the energy flux decreases rapidly, causing outer regions to become cold and frozen. Conversely, regions closer to the star receive excessive energy, leading to atmospheric loss or surface instability. This gradient creates a narrow band where conditions remain relatively balanced. Planetary atmospheres within the habitable zone play a crucial role in regulating surface temperature. Greenhouse gases can trap heat and stabilize climate conditions, while atmospheric loss can lead to extreme cooling or heating. Even within the habitable zone, variations in atmospheric composition can shift a planet between stable and unstable states. This sensitivity highlights the complexity of maintaining long-term habitability, even under seemingly favorable conditions. The presence of liquid water is often considered a key requirement for life as understood from terrestrial examples. However, the stability of liquid water depends on both temperature and pressure, which are influenced by multiple interacting systems. Within the habitable zone, these conditions can fluctuate due to orbital variations, stellar activity, and internal planetary processes. These fluctuations introduce additional layers of variability within an already narrow spatial region. Stellar variability also affects the stability of habitable conditions. Changes in stellar output, such as flares or long-term luminosity shifts, can alter the energy balance of planets within the zone. These changes may be gradual or sudden, but they introduce uncertainty into the long-term persistence of stable environments. Even stars that appear stable over short timescales can undergo slow evolution that shifts the habitable zone over millions or billions of years. The movement of a star through the galaxy can also influence the habitability of its planetary system. As the star orbits the galactic center, it may pass through regions of varying radiation density, gravitational influence, and interstellar material. These environmental changes can subtly affect planetary atmospheres and orbital stability. However, such effects occur over long timescales and remain secondary to local stellar conditions. The rarity of stable habitable conditions contributes to the overall silence of the universe. Even though habitable zones exist around many stars, the combination of necessary conditions is extremely specific. This means that regions capable of supporting stable liquid water are limited in both space and time. The narrowness of these regions reduces the likelihood of widespread biological activity across planetary systems. Within the habitable zone, planets remain separated by large orbital distances, maintaining the broader pattern of emptiness found throughout the universe. Even when multiple planets exist within a single system, only one or two may reside within the optimal range for surface liquid water. The rest exist in environments that are too extreme, reinforcing the imbalance between potential and actual habitability. The concept of habitability also depends on long-term stability rather than short-term conditions. A planet may pass through a habitable zone temporarily due to orbital changes or stellar evolution, but sustained habitability requires consistent environmental balance. This requirement further reduces the number of regions where life could persist over extended periods. As a result, habitable environments remain rare and isolated. Chemical processes within potentially habitable planets depend on the availability of elements such as carbon, hydrogen, oxygen, and nitrogen. These elements are widely distributed across the universe, but their combination into stable biological systems requires specific conditions. Even within the habitable zone, chemical complexity does not automatically lead to biological emergence. The transition from chemistry to biology remains uncertain and dependent on multiple interacting variables. The distribution of habitable zones across the galaxy reflects the distribution of stars, but not all stars provide stable or suitable environments. Some stars emit high levels of radiation or experience rapid variability, reducing the likelihood of stable conditions within their habitable zones. Others may have short lifespans that do not allow sufficient time for complex systems to develop. These constraints further limit the number of potentially stable regions. Even within favorable regions, planetary surfaces are separated by vast distances, and each system evolves independently. This isolation ensures that even if habitable conditions exist, they are not necessarily connected or synchronized across space. The lack of interaction between habitable environments contributes to the overall fragmentation of potential life-supporting regions in the universe. In this context, the habitable zone represents a rare convergence of conditions within an otherwise vast and empty structure. It is a narrow band of possibility embedded within systems that are themselves separated by enormous distances. This rarity reinforces the broader theme of cosmic silence, where favorable conditions exist only in isolated pockets, surrounded by overwhelming emptiness. Section 9. The diversity of exoplanets across the galaxy reveals a wide range of planetary types, each formed under different conditions within protoplanetary disks. These worlds include gas giants, rocky terrestrial planets, icy bodies, and extreme environments where temperatures and pressures exceed familiar limits. Despite this diversity, most planets exist in environments that are not conducive to long-term surface stability. The distribution of exoplanets shows that planetary systems often contain multiple large bodies in close or distant orbits, but the majority of orbital space remains empty between them. This separation defines the fundamental structure of planetary systems and contributes to their overall quietness. Gas giant planets dominate many systems in terms of mass, yet they occupy relatively small regions of space compared to the full extent of their orbits. These planets consist primarily of hydrogen and helium, with deep atmospheres that transition into fluid or metallic states under extreme pressure. Even though they are massive and dynamic internally, their presence in space does not significantly reduce the emptiness of the surrounding system. Their gravitational influence shapes nearby objects, but large distances still separate them from other planetary bodies. Rocky planets similar in composition to Earth are more localized in structure and often occupy inner regions of planetary systems. These planets form through the accretion of solid material and can develop complex geological and atmospheric processes over time. However, their small size relative to orbital distances means that they remain isolated within vast regions of space. Even when multiple rocky planets exist in a system, they are separated by millions of kilometers, reinforcing the dominance of empty space. Exoplanet surveys reveal that planetary systems are highly varied in architecture. Some systems contain tightly packed planets with short orbital periods, while others have widely spaced configurations with large gaps between orbits. In both cases, the total volume of empty space remains overwhelmingly larger than the volume occupied by planets. This imbalance contributes to the overall impression that planetary systems are structurally rich but spatially sparse. The detection of exoplanets relies on indirect methods such as transit observations and radial velocity measurements. These techniques identify small changes in starlight caused by planets passing in front of or exerting gravitational influence on their host stars. The need for indirect detection itself highlights the vast distances involved and the difficulty of directly observing these worlds. Most exoplanets remain invisible, except through subtle effects on their environments, reinforcing the idea that planetary systems are largely quiet on observational scales. Atmospheric composition varies widely among exoplanets, influencing their climate and potential surface conditions. Some planets possess thick atmospheres rich in hydrogen or carbon dioxide, while others have thin or nearly absent atmospheres. These differences determine how energy from the host star is absorbed, reflected, or retained. Despite these variations, atmospheric processes occur within isolated planetary environments that do not significantly affect surrounding space. Temperature extremes among exoplanets further illustrate the diversity of conditions within planetary systems. Some worlds orbit extremely close to their stars, resulting in surface temperatures high enough to vaporize rock. Others orbit at great distances where temperatures remain near absolute cold conditions. These extremes highlight the sensitivity of planetary environments to orbital position, yet they do not alter the overall emptiness between planets. Tidal locking is a common phenomenon among exoplanets that orbit closely to their stars. In this state, one side of the planet permanently faces the star while the other remains in darkness. This creates extreme temperature gradients across the planetary surface, influencing atmospheric circulation and climate patterns. Despite these dramatic conditions, tidal locking remains a localized effect that does not extend beyond individual planetary systems. The gravitational interactions between exoplanets within the same system can lead to orbital resonances, migrations, or instabilities. These interactions occur over long timescales and can reshape the architecture of planetary systems. However, even in dynamically active systems, the distances between planets remain large compared to their sizes, preserving the overall emptiness of orbital space. Some exoplanets are classified as rogue planets, meaning they do not orbit a star and instead drift freely through interstellar space. These objects further emphasize the dominance of emptiness in the galaxy, as they exist in isolation without nearby sources of energy or interaction. Rogue planets are extremely difficult to detect, and their presence is inferred through gravitational effects such as microlensing events. Their existence suggests that planetary bodies can persist even outside structured systems, but they remain widely separated in space. The study of exoplanet demographics indicates that planets are common throughout the galaxy, yet their distribution is highly uneven. Some stars host multiple planets while others appear to have none. This variability contributes to a patchwork structure of planetary systems, each with its own configuration of empty and occupied regions. Despite this abundance of planets, the total volume of space they occupy remains extremely small. Radiation from host stars continues to shape the environments of exoplanets, influencing atmospheric loss surface conditions and chemical processes. However, this radiation spreads outward into space, gradually weakening with distance and blending into the broader cosmic background. Its influence is significant near the star but becomes negligible at larger scales, leaving most of the surrounding space unaffected. The stability of exoplanetary systems depends on long-term gravitational interactions and the absence of disruptive external forces. While many systems remain stable over billions of years, others experience gradual changes that alter orbital configurations. Despite these dynamics, the systems remain separated by vast interstellar distances, ensuring that interactions between different systems are virtually non-existent. The search for exoplanets also reveals the limitations of observational methods. Many planets remain undetectable due to their size distance or lack of interaction with starlight. This observational gap reinforces the perception that much of the galaxy is quiet even when planetary systems are present. The inability to directly observe most exoplanets contributes to the broader sense of cosmic silence. In the context of the galaxy, exoplanets represent localized structures embedded within overwhelmingly empty space. Their diversity and abundance do not reduce the fundamental sparsity of the universe. Instead, they exist as isolated systems separated by vast distances, reinforcing the pattern of separation that defines cosmic structure. This separation ensures that even a universe filled with planets remains largely silent when viewed on large scales. Section 10. Planetary atmospheres represent thin layers of gas held by gravity around solid or gaseous worlds. Yet even these envelopes exist within a broader context of extreme emptiness. An atmosphere forms when a planet retains gases such as nitrogen, oxygen, carbon dioxide, hydrogen, or helium, depending on its mass, temperature, and chemical history. Although these gases create the impression of a dense environment near the surface, atmospheric density decreases rapidly, with altitude transitioning into near-vacuum conditions only a short distance above a planet's surface. Beyond this boundary space begins almost immediately reinforcing how thin the protective layer of atmospheric matter truly is in cosmic terms. The structure of an atmosphere is shaped by temperature gradients, gravitational strength, and incoming stellar radiation. Warmed by its host star, the lower atmosphere tends to be denser and more dynamic, with convection currents driving weather systems and circulation patterns. Higher layers become progressively thinner, with particles moving more freely and less frequently colliding. This gradual thinning creates a continuous transition from dense gas to near vacuum, rather than a sharp boundary between atmosphere and space. Even within this structure, most of the atmospheric volume contains relatively few particles compared to terrestrial standards. Atmospheric chemistry determines how energy from a star is absorbed and redistributed. Molecules within the atmosphere can interact with incoming radiation, absorbing specific wavelengths and re-emitting energy in different forms. This process regulates temperature and helps maintain surface conditions within certain limits. However, these interactions occur within a very thin layer compared to the size of the planet itself. Above this active region, atmospheric density becomes so low that interactions between particles become rare and sporadic. Weather systems arise from the movement of heat and moisture within the lower atmosphere. These systems can range from small localized clouds to planet-wide circulation patterns driven by rotation and solar input. Despite their complexity and energy, weather phenomena are confined to a thin shell around the planet's surface. The vast majority of space above and beyond these systems remains empty, emphasizing the limited spatial reach of atmospheric activity. Some planets possess thick atmospheres composed primarily of hydrogen and helium, while others have thin or nearly absent atmospheres due to low gravity or strong stellar radiation. In both cases, atmospheric presence does not significantly reduce the emptiness of surrounding space. Even the densest planetary atmospheres are insignificant when compared to the vacuum of interplanetary and interstellar regions. This contrast highlights the sharp transition between localized environments and the broader cosmic void. Atmospheric escape is a process by which particles gain enough energy to overcome a planet's gravitational pull and drift into space. This can occur through thermal heating, solar-wind interaction, or chemical reactions in the upper atmosphere. Over long periods of time, this process can gradually thin an atmosphere, especially on smaller planets with weaker gravity. However, escaping particles quickly disperse into the surrounding vacuum, becoming part of the broader interplanetary medium and contributing to the overall sparsity of matter. The interaction between a planet's magnetic field and its atmosphere plays a key role in protecting against atmospheric loss. Magnetic fields can deflect charged particles from stellar winds, reducing erosion of the upper atmosphere. Despite this protective effect, magnetic fields operate within a system that is already extremely sparse, where most incoming particles are widely separated in space. The effectiveness of this shielding depends on the balance between incoming energy and atmospheric density, both of which remain limited in scale. Upper atmospheric layers, such as the ionosphere, contain charged particles influenced by solar radiation. These regions can reflect radio waves and interact with space weather events, creating dynamic but thin layers of activity. Even so, the ionosphere occupies only a small fraction of the space surrounding a planet, and its particle density remains low compared to lower atmospheric layers. Beyond this region, particles become so sparse that collisions are rare, and motion is governed more by electromagnetic forces than by fluid dynamics. Exoplanet atmospheres exhibit a wide range of compositions and behaviors depending on their host stars and orbital positions. Some experience extreme heating that drives atmospheric expansion and escape, while others remain cold and stable with minimal atmospheric motion. Despite these differences, all atmospheres share the characteristic of being thin shells, around planetary bodies embedded within vast empty space. This structural consistency reinforces the idea that atmospheric systems are localized exceptions within a predominantly vacuum-dominated universe. Radiation from host stars plays a central role in shaping atmospheric evolution. High-energy ultraviolet and X-ray radiation can break molecular bonds, leading to chemical changes and atmospheric loss. Over time, this radiation can strip away lighter elements, altering the composition and density of the atmosphere. However, the effects of this radiation diminish rapidly with distance, leaving most of the surrounding space unaffected and empty. The balance between atmospheric retention and escape determines whether a planet can sustain long-term surface conditions. Larger planets with stronger gravity are more capable of holding thick atmospheres, while smaller planets lose their gaseous envelopes more easily. This balance influences planetary evolution, but does not significantly alter the emptiness of space between planets or stars. Even in systems with multiple atmosphere-bearing worlds, the separation between them remains vast. Atmospheric phenomena such as clouds, storms and jet streams occur within confined regions of the lower atmosphere. These systems are driven by energy imbalances and rotational dynamics, but remain restricted to a thin layer around the planet. Their scale, while large in planetary terms, is negligible compared to the distances separating planetary bodies. This disparity reinforces the limited spatial extent of atmospheric activity in the broader cosmic context. The transition from atmosphere to space represents one of the most gradual boundaries in nature, yet it ultimately leads to a region where particle density approaches near zero conditions. In this regime, particles move freely without frequent interaction, and collective behavior disappears. This marks the beginning of interplanetary space where emptiness dominates and atmospheric influence ceases. Even though planetary atmospheres support complex processes and dynamic behavior, they exist as thin, fragile layers within a much larger vacuum-dominated environment. Their presence does not significantly reduce the overall emptiness of the universe, but instead highlights the contrast between localized complexity and universal sparsity. This contrast is a key factor in the perception of cosmic silence. In this context, atmospheres are not barriers against emptiness, but temporary structures embedded within it. They represent regions where matter briefly becomes dense enough to support interaction before dispersing back into surrounding space. This temporary concentration of matter underscores the transient nature of structure within a largely empty universe. Section 11. Prebiotic chemistry represents the stage in which simple chemical systems begin to organize into increasingly complex molecular structures under suitable environmental conditions. This process is thought to occur on planetary surfaces, where liquid solvents, energy sources, and reactive elements are present in stable combinations over long periods of time. Even within such environments, the overall distribution of matter remains extremely sparse on cosmic scales, with chemical interactions occurring only within thin layers such as oceans, atmospheres, or mineral surfaces. These localized regions of activity exist within planets that are themselves isolated in vast regions of empty space. The formation of complex organic molecules begins with basic elements such as carbon-hydrogen, oxygen, nitrogen, sulfur, and phosphorus. These elements are widely distributed across the universe, produced in stars and dispersed through stellar winds and supernova events. However, their presence does not guarantee chemical complexity, as specific environmental conditions are required to bring them into sustained interaction. In most regions of space, these elements remain dispersed in gas or dust form, rarely engaging in the continuous reactions needed for molecular complexity. On planetary surfaces where liquid water or other solvents exist, chemical reactions can proceed more efficiently due to increased molecular mobility. Energy sources such as ultraviolet radiation, geothermal heat, or electrical discharges can drive these reactions forward, enabling the formation of more complex structures over time. Despite this increased activity, these processes are confined to limited regions of a planet's surface or subsurface environment. The majority of the planet remains chemically inactive or only weakly reactive in comparison. The transition from simple molecules to more complex organic compounds involves gradual increases in structural diversity and stability. Molecules may form chains, rings, or networks that allow for more varied chemical behavior. However, this progression is not guaranteed and depends heavily on local conditions such as temperature, pressure, and availability of reactive materials. Even in environments considered favorable for prebiotic chemistry, most molecules remain simple and short-lived, reinforcing the limited nature of chemical complexity. Energy flow within prebiotic environments plays a crucial role in sustaining chemical evolution. Without continuous energy input, complex molecules tend to break down into simpler components. This creates a dynamic balance between formation and destruction, where only a fraction of molecular interactions lead to increased complexity. This balance occurs within a narrow range of environmental conditions, further limiting the spatial extent of prebiotic activity. Mineral surfaces can act as catalysts for chemical reactions by providing structured environments where molecules can align and interact more efficiently. These surfaces can concentrate reactants and facilitate the formation of bonds that might otherwise be unlikely in open solution. However, even these catalytic effects are limited to specific regions of a planetary surface, leaving the majority of space chemically inactive. The influence of such surfaces is therefore localized and does not extend beyond planetary boundaries. The availability of stable liquid environments is a key factor in sustaining prebiotic chemistry over long timescales. Liquid water in particular provides a medium in which molecules can move, collide, and react. However, even within such environments, dilution and diffusion limit the frequency of productive interactions. This ensures that chemical evolution remains a slow and inefficient process occurring over extended periods of time. External radiation from stars can both promote and hinder prebiotic chemistry. On one hand, it provides energy necessary for driving reactions. On the other, it can razrush molecular bonds and degrade complex structures. The balance between these effects determines whether chemical complexity can be sustained in a given environment. In many cases, protective atmospheric layers or subsurface environments are required to maintain stability, further limiting the regions where prebiotic chemistry can occur. The emergence of self-replicating molecular systems represents a significant threshold in chemical evolution. These systems are capable of copying structural information with varying degrees of accuracy, allowing for the gradual accumulation of complexity over time. However, the formation of such systems is believed to require highly specific conditions that are not widely distributed across planetary environments. As a result, the transition from chemistry to biology remains uncertain and potentially rare. Even when complex molecular systems arise, they remain confined to localized environments where conditions remain stable. These systems do not spread widely across planetary surfaces without suitable transport mechanisms. This confinement ensures that any increase in complexity remains spatially limited, embedded within an otherwise inactive chemical landscape. The distribution of organic molecules in space extends beyond planets into interstellar clouds where simple compounds can form under low-temperature conditions. These environments can produce basic organic structures through interactions involving radiation and dust grains. However, the density of matter in these regions is extremely low, and chemical reactions occur at a much slower rate compared to planetary environments. This reinforces the idea that complexity is rare and spatially restricted. Over long timescales, chemical evolution on planets may lead to increasing diversity of molecular structures. However, this progression is not uniform or guaranteed, as it depends on a wide range of environmental factors. Many planetary environments may remain chemically inactive or only weakly reactive throughout their histories. This variability contributes to the overall scarcity of complex chemistry across the universe. The step from prebiotic chemistry to early biological systems represents one of the most significant transitions in natural processes. It involves the emergence of self-sustaining networks of reactions capable of maintaining internal organization. Despite its importance, this transition is thought to occur only under highly constrained conditions. As a result, even within potentially favorable environments, such systems may remain rare. In the broader cosmic context, prebiotic chemistry occupies only a small fraction of available environments. Most of the universe consists of regions where temperature, density, and radiation conditions prevent sustained chemical complexity. Even within galaxies, suitable environments are isolated and separated by vast distances, reinforcing the overall sparsity of complex chemical activity. This distribution of chemical potential contributes to the larger theme of cosmic silence. Even though the ingredients for complexity are widespread, the conditions necessary for sustained interaction are rare and localized. As a result, most regions of the universe remain chemically inactive, with only isolated pockets of activity emerging under favorable conditions. This imbalance between potential and realization defines the chemical landscape of the cosmos. In this context, prebiotic chemistry represents a delicate and localized phenomenon embedded within a vast and mostly inactive universe. Its occurrence depends on precise alignment of multiple factors, making it an exception rather than a rule. This rarity reinforces the broader structure of cosmic silence, where even the processes leading toward complexity are constrained by scale and separation. Section 12. The detection of microbial life represents a threshold where chemistry may transition into self-sustaining biological systems. Yet this possibility remains deeply constrained by observational limits and environmental requirements. On Earth, microbial life is found in an extraordinary range of habitats from deep oceans to subsurface rock layers, demonstrating that life can persist under conditions once considered extreme. However, even this adaptability does not imply that life is common across the universe. Instead, it highlights how specific and localized the conditions for life remain, even when they appear flexible in a planetary context. Microbial organisms operate at scales far smaller than planetary or atmospheric systems, yet they depend entirely on those larger environments for stability. Liquid water energy sources and chemical nutrients must remain available over extended periods for microbial ecosystems to persist. These conditions are not continuously present across planetary surfaces, but are confined to regions where temperature, pressure, and chemistry align in stable configurations. Even on a life-bearing world, large portions of the surface may remain entirely uninhabitable. The detection of microbial life beyond Earth relies primarily on indirect signatures, as direct observation is extremely difficult across interstellar distances. Scientists search for biosignatures such as specific atmospheric gases, chemical imbalances, or surface features that may indicate biological activity. However, many of these signals can also arise from non-biological processes, making interpretation uncertain. This ambiguity contributes to the broader sense that life, if it exists elsewhere, remains hidden within vast observational silence. On a planetary scale, microbial ecosystems can influence local environments through chemical cycling and energy flow. These effects can alter atmospheric composition or subsurface chemistry, but they remain confined to the regions where life is active. Even when biological activity is widespread on a planet, it does not extend beyond that planetary boundary. The influence of life therefore remains localized without direct interaction with distant systems or other planetary environments. The emergence of microbial life depends on a sequence of chemical and physical transitions that must occur in a stable environment over long periods of time. These transitions include the formation of self-replicating molecules, the development of metabolic networks, and the establishment of compartments that maintain internal organization. Each step requires specific conditions that may not be commonly met, even in environments where basic organic chemistry is present. This layered complexity further limits the probability of life emerging in any given location. Energy availability is a critical factor in sustaining microbial systems. On Earth, energy sources include sunlight, chemical gradients, and geothermal heat. Microorganisms exploit these sources to maintain internal processes and reproduce. However, in many planetary environments, energy may be either too scarce or too unstable to support long-term biological activity. This constraint reduces the number of environments where life could persist, even if it were initially formed. Subsurface environments are considered potential refuges for microbial life because they offer protection from radiation and environmental instability. Beneath planetary surfaces, temperatures can remain relatively stable, and liquid water may persist in porous rock or ice layers. These environments can provide long-term stability for biological systems, but they are difficult to observe directly. As a result, even if subsurface life exists elsewhere, it may remain undetectable from remote observation. The rarity of confirmed biosignatures beyond Earth contributes to the broader uncertainty surrounding extraterrestrial life. Despite extensive observations of exoplanet atmospheres and planetary systems, no definitive evidence of microbial life has been identified outside Earth. This absence does not rule out its existence, but highlights the difficulty of detecting such subtle signals across vast distances. Even if microbial life exists on multiple planets, the separation between these environments is so large that there is no interaction or exchange between them. Each planetary biosphere, if present, would evolve independently under its own conditions. This isolation ensures that biological processes remain confined to local environments, with no overlap or communication across interstellar space. This separation reinforces the broader structure of cosmic silence. The search for life is also limited by technological constraints. Current instruments can only detect certain types of atmospheric or surface signals, and many potential biosignatures remain beyond observational reach. This limitation means that the absence of evidence cannot be interpreted as definitive absence. Instead, it reflects the restricted window through which the universe can be observed. Even within a single galaxy, the distances between potentially habitable worlds are enormous compared to the scale of biological systems. Light and other signals take years, or even millennia to travel between stars, making any exchange of biological information effectively impossible on short timescales. This temporal and spatial separation reinforces the isolation of any potential microbial life. If microbial ecosystems exist elsewhere, they are likely to be deeply embedded within their local environments, interacting primarily with planetary conditions rather than external cosmic influences. Their evolution will be shaped by local chemistry, energy availability, and environmental stability without reference to other biological systems elsewhere in the universe. This localized development further emphasizes the fragmented nature of biological potential across space. The potential diversity of microbial life forms is vast, depending on the range of chemical and physical conditions available on different planets. However, this diversity remains theoretical without direct observation. Even if life arises in multiple locations, its manifestations would be separated by immense distances, preventing any unified biological presence at cosmic scale. In this context, microbial life represents a highly localized phenomenon embedded within an overwhelmingly large and empty universe. Its presence, if it exists beyond Earth, would not alter the large-scale structure of cosmic silence. Instead, it would remain confined to small regions where conditions briefly align to support complex chemistry and biological stability. The challenge of detecting microbial life underscores the limits of observation in a vast universe. Even if life is widespread, its signals may be too faint, too rare, or too localized to be distinguished from background processes. This creates a situation where biological activity could exist without contributing significantly to observable cosmic structure. In the broader cosmic framework, microbial life represents a rare and isolated expression of complexity within an otherwise sparse and silent universe. Its emergence depends on precise conditions that are not guaranteed to occur frequently, and its persistence is confined to stable planetary environments. This rarity reinforces the overarching theme of cosmic silence, where even life itself may be a localized exception rather than a universal norm. Section 13. The emergence of intelligent life marks a further step in complexity, where biological systems develop advanced information processing adaptation and the ability to modify their environment in deliberate ways. On Earth, this transition occurred through long evolutionary processes driven by natural selection, environmental pressures, and increasing neurological complexity. However, even within a planet where intelligence has arisen, it remains confined to a thin surface layer and a narrow set of ecological conditions. The vast majority of the planet remains uninhabited or only sparsely influenced by biological activity. Intelligence, as understood through technological capability, depends on stable energy sources and long-term environmental continuity. On planetary scales, this often means access to sunlight, chemical energy, or geothermal processes that can sustain metabolic and cognitive systems over extended periods. Even with these resources available, the development of intelligence is not guaranteed. It requires a long chain of evolutionary steps that may be disrupted by environmental changes, extinction events, or random variation. This fragility limits the frequency with which intelligence may arise in the universe. The presence of intelligent life does not significantly alter the large-scale structure of a planetary system. Even technologically advanced civilizations occupy extremely small volumes compared to the size of their host planets and surrounding space. Their activity is concentrated in localized regions, while the majority of planetary surface and surrounding orbital space remains empty or only weakly affected. This spatial limitation ensures that intelligence does not transform the broader emptiness of space. Communication between intelligent systems, if it exists beyond a single planet, is constrained by the finite speed of light. Signals such as radio waves or laser transmissions travel at fixed speeds, meaning that even the nearest star systems are separated by years of delay. Over galactic distances, these delays become so large that real-time interaction becomes impossible. This introduces a fundamental temporal separation between any potential intelligent civilizations, reinforcing their isolation. Technological signals, often referred to as technosignatures, include artificial radio emissions, atmospheric pollutants, or structured energy patterns that may indicate the presence of advanced systems. These signals, however, weaken rapidly as they spread through space. Even powerful transmissions become indistinguishable from background noise over interstellar distances. This rapid dispersion contributes to the difficulty of detecting intelligent life beyond a local region. The development of technology introduces new forms of energy use, but these remain confined to planetary environments. energy consumption on a planetary scale is still minuscule compared to the total energy output of a star or galaxy. Even large-scale industrial activity does not significantly alter the energy balance of a planetary system when viewed from a cosmic perspective. As a result, technological civilizations remain effectively invisible on large scales. The timing of intelligent civilizations is also a critical factor in their detectability. Civilizations may emerge at different times throughout cosmic history, but the windows during which they produce detectable signals may be relatively short compared to astronomical timescales. This temporal mismatch reduces the likelihood that two civilizations will overlap in detectable phases. Even if many civilizations exist, they may rarely coincide in ways that allow communication. Planetary habitability windows are influenced by stellar evolution, as stars gradually change in brightness and temperature over time. These changes shift the conditions necessary for stable environments, potentially limiting the duration during which intelligent life can persist. Once conditions move outside suitable ranges, civilizations may decline or disappear entirely. This further reduces the probability of sustained widespread intelligence across the galaxy. The distribution of potentially habitable planets across the galaxy is uneven, and even within habitable zones, environmental stability varies. Some planets may experience frequent catastrophic events, while others remain stable for longer periods. This variability ensures that intelligent life, if it exists, is scattered across isolated environments rather than forming continuous networks. The resulting separation reinforces the fragmentation of potential communication. Even within a single planetary system, distances between objects remain large enough to limit interaction. Communication between planets would require significant energy and time delays, making sustained exchange difficult. This internal separation mirrors the larger interstellar isolation experienced between star systems, reinforcing a consistent pattern of distance-driven silence at multiple scales. The concept of observational silence arises not from the absence of intelligence, but from the limits of detection and communication. Intelligent activity may exist without producing signals strong enough to propagate across interstellar space. Even if such signals exist, they may be indistinguishable from natural background processes by the time they reach distant observers. This creates a universe where intelligence may be present but effectively hidden. The energy required to maintain large-scale communication across interstellar distances increases rapidly with distance. Signal strength decreases as it spreads, requiring increasingly powerful transmission to remain detectable. This physical limitation ensures that long-range communication is inefficient, further restricting the potential for widespread interaction between civilizations. In addition to physical constraints, environmental noise such as cosmic radiation, background radiation, and natural astrophysical signals complicates the detection of artificial patterns. These overlapping signals create a complex background in which weak artificial emissions can easily be lost. This further contributes to the difficulty of identifying intelligent activity across space. If intelligent civilizations are rare, short-lived, or widely separated in time and space, their combined contribution to observable cosmic structure remains minimal. Even a galaxy containing multiple intelligent systems would appear largely unchanged at large scales. Their presence would not alter the distribution of matter radiation or gravitational structure in any detectable way beyond their immediate surroundings. The isolation of intelligent life therefore mirrors the broader patterns seen throughout the universe, where structure exists but remains widely separated by empty space. Intelligence, like stars and planets, becomes another localized phenomenon embedded within vast regions of emptiness. Its influence is significant locally but negligible globally. In this context, the silence of the universe emerges not from the absence of intelligence, but from the extreme separation of conditions required for its emergence and detection. Even when intelligence exists, it is constrained by distance, time, and energy limits that prevent it from forming a connected or observable whole across cosmic scales. Section 14. The study of technosignatures focuses on identifying physical evidence of technological activity beyond Earth, yet these potential signals are deeply constrained by distance, dispersion, and background noise. Technosignatures can include artificial radio emissions, laser pulses, atmospheric chemical imbalances, or large-scale energy usage patterns. However, all of these signals must travel across interstellar space, where they spread out, weaken, and gradually blend into the natural background of cosmic radiation. Over vast distances, even structured emissions lose their distinctiveness, becoming increasingly difficult to separate from random astrophysical processes. Radio waves, one of the most commonly considered carriers of interstellar communication, propagate at the speed of light, but disperse as they expand through space. This dispersion reduces signal intensity dramatically with distance, following a geometric weakening that makes detection extremely challenging beyond nearby star systems. Even powerful transmissions intended for long-range communication would fade into the background noise of the galaxy after traversing only a small fraction of its diameter. This physical limitation ensures that most artificial signals remain confined to local regions. Laser-based communication offers higher precision and directionality, but it still faces similar constraints. While tightly focused beams can travel farther without spreading, they require exact alignment between transmitter and receiver. Any slight deviation in direction causes the signal to miss its target entirely. Additionally, over interstellar distances, even laser beams become subject to scattering by interstellar dust and gas, further weakening their detectability. These limitations make directed communication across the galaxy highly improbable. Without extremely precise coordination, atmospheric technosignatures represent another potential indicator of technological activity. These include industrial pollutants or artificial chemical compounds that accumulate in a planet's atmosphere. On Earth, such signatures are detectable because instruments can analyze light passing through the atmosphere. However, at interstellar distances, these signals are extremely faint and require advanced observational capabilities to distinguish from natural atmospheric processes. Even then, interpretation remains uncertain due to overlapping natural chemical pathways. Large-scale energy use, sometimes described as planetary or stellar engineering, could in principle produce detectable waste heat or unusual radiation patterns. However, current observations of distant stars and galaxies show no clear evidence of such large-scale modifications. If such activities exist, they are either rare, short-lived, or below the threshold of detectability. This absence of clear signatures contributes to the broader perception of a quiet universe. The interstellar medium itself introduces significant interference in signal propagation. Dust particles, ionized gas, and magnetic fields can scatter or absorb electromagnetic radiation, altering or weakening any structured signal passing through them. Over long distances, this cumulative interference increases, making it increasingly difficult to preserve the original information content of any transmission. As a result, even carefully designed signals degrade into indistinct noise. Background cosmic radiation further complicates detection. The universe is filled with natural emissions from stars, pulsars, quasars, and the cosmic microwave background. These sources create a constant background of electromagnetic activity that any artificial signal must compete against. In most cases, weak technosignatures would be indistinguishable from this natural background without highly targeted analysis. The timing of signal emission also plays a critical role in detectability. A civilization may transmit signals for only a limited period during its technological development. If this period is short compared to the time required for signals to traverse interstellar distances, those signals may never be detected by another civilization. This temporal mismatch further reduces the likelihood of observing technosignatures even if they exist. The geometry of space introduces additional constraints. Signals radiate outward in expanding spheres, unless tightly directed, meaning that their energy is distributed over increasingly large volumes. This rapid dilution ensures that signal strength decreases quickly with distance. Even highly energetic transmissions become diffuse and weak when spread across interstellar scales. Some theoretical proposals suggest that advanced civilizations might use non-electromagnetic methods for communication or signaling, such as neutrino beams or gravitational waves. However, these methods face their own detection challenges due to extremely weak interaction with matter or limited current technological sensitivity. As a result, they remain speculative and unconfirmed as practical communication methods. The search for technosignatures relies heavily on observational surveys of nearby stars and exoplanet systems. These surveys analyze light spectra, radio emissions, and infrared excesses for anomalies. Despite extensive monitoring, no definitive artificial signals have been confirmed. This absence does not necessarily indicate absence of intelligence, but it reinforces the difficulty of detecting weak or distant activity. Even if technosignatures exist, their distribution across the galaxy is likely sparse and uneven. Civilizations may be separated by vast distances, or may not overlap in time, reducing the probability of simultaneous detectability. This separation ensures that any technological signals are isolated events, rather than continuous interconnected communication networks. The vastness of space itself acts as a filter that removes most detectable traces of activity. Only the most powerful or persistent signals can survive long enough to be observed at great distances. Even then, distinguishing them from natural phenomena requires careful analysis and repeated confirmation. This filtering effect contributes significantly to the perceived silence of the cosmos. Technosignatures also depend on the longevity of technological civilizations. If such civilizations are short-lived, their signals may fade before reaching distant observers. If they are long-lived but technologically conservative, they may not produce strong or detectable emissions at all. Both scenarios reduce the likelihood of observing clear evidence of technological activity. In the broader cosmic context, the absence of confirmed technosignatures reinforces the idea that intelligent activity, if it exists, is not widespread or easily observable. This absence does not necessarily imply non-existence, but it does highlight the extreme difficulty of detection across interstellar distances and timescales. The combination of signal dispersion, background noise, temporal mismatch, and spatial separation creates a universe where technological activity can easily remain hidden. Even if civilizations are present, their signals may never converge within detectable range of one another. This structural limitation contributes directly to the broader theme of cosmic silence. In this framework, technosignatures represent one of the most fragile and easily lost forms of cosmic information. They depend on precise conditions for both emission and detection conditions that are rarely satisfied across the vast scales of the universe. As a result, the cosmos appears quiet not because it lacks activity, but because most forms of structured communication are lost long before they can be observed. Section 15. Cosmic time introduces a final and fundamental layer to the silence of the universe, where even if civilizations, signals, or structures exist, they are separated not only by distance, but also by vast intervals of time. The universe is approximately 13.8 billion years old, and within this immense span the emergence of stars, planets, chemistry, and biological systems occurs in staggered phases across different regions. Because no single process is synchronized across all space, the development of complexity unfolds independently in isolated pockets, each shaped by its own local history. Stars form live and die over timescales ranging from millions to billions of years, continuously reshaping the chemical landscape of galaxies. Each generation of stars produces heavier elements that are dispersed into space, enabling later generations of planetary systems to form with increasingly complex materials. However, these cycles occur in different regions at different times, meaning that the conditions for life and intelligence are not globally aligned. Some regions may reach suitable conditions early, while others may do so much later or not at all. Planetary systems themselves evolve over long durations with stable periods that may last billions of years before gradual changes in stellar brightness or orbital dynamics alter their environments. Within these windows of stability, life may emerge and evolve, but only for limited intervals determined by local conditions. Once those conditions shift, the opportunity for sustained biological or technological development may diminish or disappear entirely. This temporal variability ensures that even within the same galaxy, habitable periods are fragmented across time. The concept of observational delay further deepens this separation. Light from distant regions takes millions or even billions of years to reach any observer, meaning that the universe is always seen in a mixture of different historical states. Some regions are observed as they were in early cosmic history, while others are seen in more recent stages. This layered view prevents any unified perception of the universe at a single moment, reinforcing the sense of disconnection between events. If intelligent civilizations arise, they do so within narrow time windows defined by planetary and stellar stability. These windows may not overlap with those of other civilizations even within the same galaxy. As a result, two civilizations capable of communication may never exist at the same time, or may exist so far apart in time that their signals never intersect in observable space. This temporal mismatch significantly reduces the probability of contact. The finite speed of light ensures that all communication across space is delayed, creating a permanent gap between emission and reception. Even if signals are transmitted continuously, they arrive at destinations long after the originating conditions have changed. This means that any exchange of information is always historical, rather than immediate, reinforcing the separation between regions of activity. Galactic evolution itself occurs over billions of years, with spiral arms, rotating stars migrating, and clusters forming and dispersing. Despite this constant motion, the overall structure of galaxies remains relatively stable on shorter timescales. This stability contrasts with the long-term changes that gradually reshape the galaxy, but these changes are too slow to create immediate large-scale connectivity between regions. On the larger scales, the expansion of the universe further stretches distances between galaxies, increasing separation over time. Distant galaxies move away from each other as space itself expands, reducing the likelihood of future interaction. In some regions, this expansion is so strong that galaxies will eventually move beyond observable reach, creating permanent horizons that limit communication and observation. Even within galaxies, the combination of spatial and temporal separation ensures that interactions between distant systems are rare. Stars and planetary systems evolve independently, and any signals or effects they produce are constrained by both distance and time delays. This independence creates a fragmented structure where local activity exists without global coordination. The silence of the universe therefore emerges from the layering of multiple forms of separation. Spatial distance limits interaction. Temporal delay prevents synchronization, and evolutionary differences ensure that conditions rarely align. Together, these factors create a cosmos where activity exists everywhere, but meaningful connection is extremely rare. From this perspective, the so-called Great Silence is not a single phenomenon, but the cumulative effect of scale, distance, time, and probability. Each layer of the universe operates on its own timescale, with little overlap between them. Even when similar processes occur, they are separated by such vast intervals that they rarely influence one another directly. The universe contains continuous activity at every level, from subatomic interactions to galactic evolution. However, this activity is distributed across a framework that prevents coherent global communication. Signals fade, structures drift, and conditions change before alignment can occur. This creates a fundamental mismatch between existence and observability. In this context, silence is not emptiness but separation. The universe is full of events, but those events are isolated in both space and time. The Great Silence emerges naturally from this isolation, as a consequence of physical laws governing light expansion and evolution. It is not imposed but constructed through scale. As the universe continues to evolve, this separation may increase further. Expansion will continue to stretch, space stars will continue to age and fade, and sources of radiation will become more diffuse. Over immense timescales, regions of activity may become even more isolated, reinforcing the quiet structure already present. The final result is a universe that is active in every direction, yet fundamentally disconnected at large scales. Each region carries its own history, its own processes, and its own potential for complexity, but these remain largely inaccessible to others. The silence that emerges is therefore not a lack of existence, but a reflection of profound cosmic distance in both space and time.